every new programmer eventually hits the exact same wall. You open a tutorial on data structures and algorithms, see a flood of complex equations, and it feels like staring into the void. A common perspective frames DSA as a barrier for big tech interviews, a test of whether you can memorize thousands of solutions or solve complex math on the fly. In reality, trying to memorize code is often the least effective way to learn. This field relies on pattern recognition and the ability to decompose a problem into its logical parts. While it is heavily tested in interviews, its real-world purpose is much more practical. This is the toolkit used to keep software from stalling, lagging, or crashing the second it has to process massive amounts of data. Once the subject is organized into a 5-phase roadmap, the learning process shifts from a chaotic struggle into a logical, manageable sequence. Phase 1 starts with the foundation. Choose one programming language, like C++, Java, or Python, and master its syntax, loops, and object-oriented principles. You need to be comfortable with the logic of the language before attempting to build complex structures with it. This chart illustrates Big O notation, measuring time and space complexity. It contrasts a flat, efficient horizontal line, representing O of 1, against a steeply accelerating O of n squared curve. Feeding that steep curve a million users will exhaust system memory and trigger a crash. Writing basic logic and accurately measuring its efficiency is the mandatory ground floor of software engineering. With a solid foundation, we enter Phase 2, linear data structures. Here, you learn how to store data in a straight line, starting with the most basic memory blocks, arrays and strings, and practicing how to traverse them. While arrays force data into a rigid sequence, a linked list uses memory pointers to connect individual nodes. Stacks group these nodes on a last-in, first-out principle, like stacked plates. Queues operate first-in, first-out, like a ticket line. Mastering these linear structures provides the core vocabulary required to organize raw data in a computer's memory. Now that our data is stored, Phase 3 introduces foundational algorithms. You start by learning the mechanics of moving data around through basic sorting methods like bubble and insertion sort, before upgrading to efficient techniques like merge and quicksort. We upgrade from slow linear search, checking every item, to binary search, which instantly halves the data repeatedly to find the target. Next, paradigms like two-pointers and sliding window smoothly analyze data subsets, bypassing clumsy brute force solutions. Data structures provide the organization, while these algorithms provide the logic. Together, they allow you to transform raw data into a tool with speed and utility. Real-world data is rarely a straight line. Phase 4 tackles nonlinear data structures, starting with hash tables for instant key-value pair lookups and the logic required to handle data collisions. From there, we build basic binary trees, then introduce self-balancing mechanisms like AVL or red-black trees to maintain organization as data is added. Finally, this expands into graphs, mapping out vast networks of vertices, edges, and adjacency lists. Mastering these nonlinear structures allows you to accurately map and navigate the complexity of human relationships, shipping routes, and sprawling real-world systems. We finally reach Phase 5, advanced algorithms. This begins with recursion, writing functions that call themselves. It is a mandatory technique for effectively traversing the complex trees and graphs we just built. You apply that recursion to breadth-first and depth-first search methods, while also practicing greedy algorithms, where the code evaluates and selects the locally optimal choice at every single step. This leads to dynamic programming, where you store the results of overlapping subproblems, and backtracking. By exploring paths and instantly retracting from dead ends, you rapidly narrow down correct solutions. These advanced algorithms are cognitive frameworks built to solve the hardest computational puzzles efficiently. Approaching data structures and algorithms as a sequential progression provides a concrete alternative to the stress of brute force memorization. Mastering these phases equips you for the technical demands of high-level interviews and the practical challenges of building software that remains stable under heavy load. The journey starts with a single decision. Choose your foundational language for Phase 1, C++, Java, or Python, and drop your choice in the comments below. Let's get to work.